Testing wireless devices has always been a challenge, and one complicated by the essential nature of free space, an uncontrolled and uncontrollable environment. The fundamental nature of radio propagation involves a wide range of complex variables, and traditional test methodologies are often rendered ineffective by the essential variability, inconsistency, and potential for interference always present in an open-air environment. Fortunately, there is a solution that not only addresses the variable and unpredictable nature of traditional wireless test strategies, but also for the first time enables development, test, QA, and deployment engineers to understand and predict the performance of wireless devices of all types in the real world. And it's available now from octoScope. In this video, we will discuss wireless test strategies, the essential requirement for test automation, and how octoScope's octoBox testbed provisions an optimal wireless testing environment. We will show how performance, behavioral, and system tests can be set up using the stackable and highly configurable octoBox testbed. Here we see a broad range of tests important in optimizing wireless products. Throughput is the most common performance test, but there are many other important performance metrics. For example, voice and other real-time transmissions such as video conferencing and gaming have stringent requirements regarding packet error rate and jitter. Access point performance testing includes validating association capacity and forwarding rate. We will explain these metrics further in this video. Behavioral tests verify the implementation of mobility and adaptation functions crucial to realizing optimal performance. Focus tests like data rate adaptation, channel adaptation, and roaming can help shine a light on the causes of poor throughput and packet error rate performance. System tests validate the behavioral, interoperability, and coexistence protocols that must work properly to achieve reliable wireless performance and happy users. Given the complexity of wireless testing and the number of variables impacting each test metric, it is crucially important for test and development engineers to work in an RF environment completely isolated from outside interference and where the test parameters can be individually controlled via test automation software. The octoBox API includes control over important parameters, including traffic, interference, orientation, motion, path loss, and multipath. This slide shows the octoBox testbed devices in the bottom row and their corresponding functionality in emulating the variables for the tests. Wireless metrics are a function of many variables. First, let's look at the RF environment. Wireless performance and behavior vary as a function of distance and obstacles such as walls, which limit the operating range of wireless networks. The octoBox testbed utilizes our Quad-10 programmable RF attenuator to emulate distance and walls. The Quad-10 incorporates 4 programmable attenuators to form a 4x4 MIMO link and enables you to test throughput, jitter, and packet error rate versus range, as well as other aspects of performance. Effective radiated energy is non-uniform and performance will vary with antenna orientation. It's thus critical for wireless test engineers to measure throughput and other performance metrics with a variety of device orientations. The octoBox testbed includes a built-in anechoic turntable that precisely controls device orientation in 1-degree steps or via a set revolution per second rotational speed. octoBox throughput test software can plot performance versus range as well as versus orientation using a polar plot. The octoBox throughput script controls traffic, turntable, and programmable attenuators and automatically creates Excel plots of the throughput. Throughput in megabits per second is plotted versus attenuation and versus device orientation with respect to test antennas in the octoBox. This particular plot shows an antenna pattern exhibiting deep nulls. These measurements are taken at 5 decibel attenuation steps and 30-degree rotation steps. The script records throughput at each rotation step versus the desired range of attenuation steps. And of course, step sizes and the throughput measurement period are completely programmable. This is an example of a throughput versus range plot. Here, rotation can be employed to average throughput versus device orientation. For example, you can specify a 1-minute measurement period with 1 revolution per minute rotation speed. The device is rotated over a full revolution during each 1 minute of throughput measurement, allowing you to average throughput versus time versus orientation simultaneously. Averaging versus time versus path loss and versus orientation is vital because throughput and other wireless metrics are statistical in nature and very relative to each other, and can be impossible to understand without the right testing environment and equipment. The octoBox multipath emulator, or MPE, accurately models multipath. The MPE is completely broadband with a power delay profile matching that of the IEEE 802.11 model of a typical house. The broadband nature of the octoBox multipath emulator allows you to run multi-channel system tests and to validate automated channel adaptation algorithms, something that would be impossible using a traditional fader that only supports one channel at a time. The octoBox iGen interference generator emulates interference from adjacent Wi-Fi cells as well as other common sources of interference. Here we see the spectrum of Wi-Fi traffic interference generated by the iGen. This measurement using the Tektronix mixed domain oscilloscope shows an injection of 40 MHz wide Wi-Fi interference into an 80 MHz Wi-Fi channel. If you inject such interference into the control channel of a system under test, this system is expected to adapt by possibly changing the operating channel. Using its built-in frequency synthesizer, the iGen can generate common frequency hopping signals such as Bluetooth or frequency swept signals such as microwave ovens. This measurement shows a Bluetooth low energy signal interfering with the Wi-Fi signal from the system under test. The iGen's traffic and waveform are fully programmable via a browser or via a test automation application programming interface. Traffic interference is generated by replaying industry-standard PCAP files, which are supported by common sniffers. When replaying PCAP files, the iGen offers powerful programmability, including interpacket gap, priority, modulation coding scheme, 802.11 standard, channel width, contention, and more. Waveform interference, as shown on the right, includes a variety of common waveforms such as Bluetooth, Zigbee, radar, and more, and can be further customized via user-loadable CSV files. The next environmental variable that impacts wireless performance is motion. Motion triggers roaming and data rate adaptation, and thus directly impacts all performance and behavior metrics of a device or system under test. Motion can be emulated by ramping the Quad 10 programmable attenuator to precisely emulate signal loss versus time. The ramping rate can be accurately controlled to emulate velocity of motion. Motion can also be emulated by rotating the device on a turntable at a programmable RPM speed to emulate Doppler. Almost all test metrics vary with channel frequency and channel width. The octoBox testbed is broadband, supporting a frequency range from 700 MHz to 6 GHz, and allowing you to sequence through channel frequency and channel width settings while obtaining performance and behavior measurements. The wide octoBox frequency range accommodates practically all cellular, Wi-Fi, and other unlicensed services. octoBox also supports the Automotive Direct Short Range Communications, or DSRC, band. When testing a client device, you need one or more access point partner or golden devices to form a test network. For this, you can use real APs, or you can use the Octoscope Octopal golden partner device that can emulate any type of AP. Octopal is a key element in a small benchtop testbed. It is fully isolated and can be mounted on the side of the octoBox along with other building blocks such as Quad 10 and iGen. When testing an access point or a router, you will need one or more client devices. It is important to test router association capacity by provisioning or emulating multiple clients. And it is important to measure the router's forwarding rate using a traffic source exhibiting a high packet rate from multiple clients. Octopal can serve as a golden reference partner device for such a test. You can also add the multipath emulator to make the conditions even more challenging. Wireless devices automatically adapt to hostile conditions such as path loss, interference, and multipath. If adaptation protocols are inadequately implemented, performance will be impacted. Thus, it is important to verify adaptation behavior in a focused test. The key adaptation technique is data rate or modulation coding scheme adaptation. The plot shown here demonstrates data rate adaptation as a function of signal strength, or RSSI. The device under test adapts to lower data rates as expected with decreasing signal power, but the higher data rate is not recovered even once the original signal power is restored. Other forms of adaptation include automated channel selection, such as a change in channel in response to interference, and band steering, which, for example, might move slow and legacy devices to the 2.4 GHz band while allowing only high-performance 802.11n and AC devices to operate in the 5 GHz band. Now let's take a look at the most important test metrics and the variables that impact these tests. Throughput is the most common test and should be measured in an RF environment where the parameters that impact it, such as range, orientation, multipath, interference, and more, can be configured in a controlled manner. Forwarding rate is the speed with which a router can move packets. The most challenging test here is to see if the router can keep up with the highest possible packet rate supported on the client side. The fastest packet rate traffic is a stream of the shortest packets sent with the shortest interpacket gap. The number of devices active in the network impacts the size of the lookup table the router keeps and is also an important variable in the forwarding rate test. Low packet error rate is important for services such as voice, video teleconferencing, and automotive DSRC communications. Such services send short packets that result in low throughput, and hence throughput is not an appropriate measurement here, but these packets must be reliably received for high quality of service to be achieved. Jitter is likewise critical for voice and real-time video services. These services expect isochronous traffic characterized by packet delivery at very regular intervals. If the time interval between packets varies, the voice signal sent over the wireless channel may be distorted. Data rate adaptation underlies most performance issues and must be tested in a focused manner. The association capacity of an access point is typically tested with emulated clients of different types. octoPAL can be very helpful with this test. The metric of receiver performance requires a golden partner device, such as octoPAL, capable of transmitting at a specified fixed modulation coding scheme. Receiver sensitivity is measured versus path loss and MCS and requires the extremely well-isolated environment that the octoBox delivers. Receiver sensitivity should be measured with and without adjacent channel interference, since adjacent channel interference can significantly impact this important metric. To put it all together, test engineers face a significant challenge in performing many important tests, including throughput, forwarding rate, packet error rate, jitter, data rate adaptation, association capacity, and receiver performance. The large number of tests required depends on a similarly large number of variables, calling for sophisticated test automation. Test automation is critical for comprehensive testing of all important parameters. Thorough laboratory testing of each metric versus each parameter that impacts the metric will help assure good performance in the field. But to get through what is in reality an exponential number of tests, engineers must have access to appropriate test automation. Test automation software available from Octoscope precisely controls the RF environment of the octoBox testbed and the integrated instruments such as the iGen, Quad-10, and octoPAL. Octoscope's test automation software also controls off-the-shelf devices and traffic generation. Here we see an example of the octoBox throughput test parameters. Each setting is available via both a browser and an application programming interface. octoPAL is a key instrument for many important tests, including throughput, packet error rate, jitter, data rate adaptation, channel adaptation, and other tests. The octoBox testbed is stackable and configurable. All octoBox models provision an excellent MIMO environment for devices in the test network, while the stackable modules, such as the multipath emulator, iGen, and octoPAL, are connected as needed for a variety of tests. Shown here is an 8x8 MIMO test configuration that supports both multi-user MIMO and beamforming. Multi-user MIMO is difficult to test in open air or in walk-in isolation chambers due to the motion of humans, but octoBox offers a completely repeatable environment for MU MIMO testing. Here we see an example of a roaming test configuration, which is a focus of Octoscope's earlier video available on YouTube. You can configure the octoBox for the comprehensive coexistence testing that is becoming increasingly important with the emergence of unlicensed LTE. This example shows a testbed configured as two neighboring cells, Wi-Fi and LTE. You can test how real Wi-Fi and LTE devices interact and use the octoPAL and iGen for controlled traffic and interference generation. And you can flexibly and easily set up wireless test networks emulating multiple rooms in a house with real or emulated devices placed at precise range with respect to one another in the test network. Here we see a large octoBox configuration being used to evaluate video performance. The octoBox comes in two convenient sizes, both stackable for a variety of test configurations, including single-box PAL benchtop test beds relying on the octoPAL as the golden partner device in combination with the iGen and Quad-10 for comprehensive test suite support, including multipath emulation if desired, and a variety of completely isolated test modules to help configure the test topology and traffic. All octoBox test modules are powered and controlled via Power over Ethernet, and all interfaces are carefully filtered to maintain complete isolation from outside interference. Filtering of all copper lines entering the test space is key to maintaining isolation, since metallic Ethernet, USB, HDMI, and other such cables are essentially antennas picking up and carrying interference between the outside environment and the test environment. This slide shows high-speed data filters located in the back of the octoBox. A waveguide filter is also provided for fiber optic connections. Another important detail of the test bed is built-in high-gain antennas, easily aimed and polarized for optimum MIMO conditions. Features include the flexible mounting of a variety of antennas, plastic brackets and shelves for arranging devices while maintaining stable anechoic control of the over-the-air test environment, layers of RF absorber built into shelves to emulate distances and walls between devices in the test bed, and even the octoBox turntable is anechoic with a plastic platter and shaft to minimize uncontrolled reflections inside the octoBox. In other words, the octoBox can model a large house in a very small footprint and can be easily located in each engineer's cubicle for efficient development and test progress. And finally, the octoBox test beds are fully configured at the factory and shipped in a crate with a built-in ramp. octoBox test beds are designed to easily roll through the smallest standard doors and are mounted on military-grade heavy-duty casters, so you can wheel your octoBox out of its crate and start testing. octoBox is being used by wireless operators, device manufacturers, and chipset vendors to test Wi-Fi, LTE, Zigbee, Bluetooth, and other wireless technologies. With its complete isolation and consistent test environment in use in labs around the world, the octoBox solution is highly praised by a diverse base of users. Please visit the Octoscope website for more details on the octoBox, customer endorsements, and an extensive collection of videos, white papers, and test reports focusing on today's key wireless issues.